In this lecture, we are going to discuss a fundamental concept in finance, alpha and beta. Unfortunately, many resources frame the concept of alpha and beta as mysterious and overly mathematical. In fact, as you'll see, alpha and beta derive from one of the simplest ideas in machine learning. There's nothing mysterious about them at all. So, there is a good reason why this lecture goes right after our discussion on correlation. As you recall, when two stocks are perfectly correlated, a scatter plot of the returns will show a perfectly straight line. They can either be perfectly correlated or perfectly anti-correlated. That just means the line will go up and to the right or down and to the right. For students of machine learning and statistics, the first algorithm we always learn about is linear regression. Another name for this is the line of best fit. This is a model that we use when we observe linear correlation between some input and some output, kind of like how we do right now. The line serves as a predictive model. That is, I can ask a question like, if I work for 3 years, what will be my salary? If I work for 4 years, what will be my salary? In fact, many students learn about this technique in high school, but without being told that they are doing statistics. In grade school, you usually take a ruler and try to find the line of best fit visually. Of course, as you progress to college and beyond, we use calculus and maximum likelihood estimation in order to find this line more precisely. Since this course is not about linear regression, I'm not going to bore you with the details about how the algorithm works, but rather I'm going to focus on the modeling aspect. In grade school, we learned that a line is expressed as y equals mx plus b. In this form, x represents the input variable, which goes along the horizontal axis. Y represents the output variable, which goes along the vertical axis. M represents the slope, which tells us how steep the line is, and b is the y-intercept, which tells us where the line crosses the y-axis. In other words, b is the value of y when x is 0. Let's see how this applies in finance. Well, you've already seen that we can draw a scatter plot between the returns of pairs of stocks. Most typically, we put the return of the market on the x-axis and the return of some other asset on the y-axis. For example, maybe we want to compare Apple's stock return with the market or the stock return on some retirement fund with the market. Another option is to compare one stock with another stock, but let's assume for this lecture that we want to compare against the market. Typically, it's conventional to assume that the market is represented by the S&P 500. As you recall, the symbol for this is SPY. Now let's say we take the stock returns for Apple, we take the stock returns for SPY, we create the scatter plot, and then we draw the line of best fit. Well, it turns out that alpha and beta are nothing but the intercept and slope of this line. That is, beta tells us how much Apple moves relative to the market. If beta equals 2, for example, and the market goes up by 1%, then Apple is predicted to go up by 2%. If the market goes down by 5%, then Apple is predicted to go down by 10%. On the other hand, alpha is how much better Apple is, irrespective of the market. For example, an alpha of 1% means that the return for Apple was 1% better than the market for the period in which we looked at the returns. A positive alpha means Apple has performed better than the market. A negative alpha means Apple has underperformed the market. Conceptually, we want to achieve high alpha because we want to outperform the market. So how does this work in code? As mentioned, in this class, we won't be overly concerned with implementing machine learning models unless it's absolutely necessary. So we will turn to our old friend scikit-learn. In general, scikit-learn models are designed for vector observations. That is, you would try to predict an output y based on multiple x's. An example of that would be something like r sub I, the return on asset I, is equal to beta 1 times r1 plus beta 2 times r2 plus beta 3 times r3 plus alpha. So you have 3 different returns as your predictors, rather than just the one return, which is the market. In fact, this is a more advanced type of model in finance, known as a factor model. These will probably be outside the scope of this course. In any case, the point of this is to say that we can't simply pass in a one-dimensional array of returns, since in scikit-learn, our data is expected to have shape n by d, where n is the number of samples and d is the number of features. In our case, n is the number of days for which we have stock returns, and d is just 1 because we're comparing to just the market. So in order to use scikit-learn for linear regression, we need to make our array of returns a 2D array of size n by 1 rather than a 1D array of size n. After that, we use the scikit-learn API as usual. First, we create an instance of the model. Second, we call model.fitxy. In this case, x is the returns on the market, and y is the returns on whatever stock we are comparing to the market. Third, if we want to make predictions or draw the line of best fit after fitting the model, we call model.predictx. To summarize this lecture, we just learned about the fundamental financial concepts of alpha and beta. We learned that these are nothing but the parameters of a line of best fit. Alpha is how much better or worse an asset performs compared to the market, and beta tells us how much an asset moves relative to the market. Now it makes sense why companies often name themselves after the term alpha. We saw an example of that earlier in the course with Alpha Vantage, a data platform. Another example is Bridgewater Pure Alpha, a famous hedge fund. Note that these say nothing about how accurate the model is or how noisy the data around the line is. For that, we would need to look at the correlation. In the next lecture, we look at how to find alpha and beta in code.